All right, now the recording is started, and I will share my screen. Let's see. Okay, there we go. Could someone confirm to me, perhaps in the chat, that you're seeing Agda? Yes. Font size, can you read it? Okay. Good. Otherwise, just let me know. Awesome. All right, so welcome to the problem solving session for the exercises corresponding to the fourth Agda lecture of the HoTTEST Summer School 2022. This one is about higher inductive types. So in the lecture, we saw the prime example was the circle, which consists of a point and, let's see, it consists of a point and a path from that point to itself, which you should think of as the loop of the circle. So this one, we use the identity type here. So this is really relies on the homotopy type theory interpretation, the homotopy interpretation of type theory. So we think of identity types as paths. Right. So I will just go through the exercises. We'll see. I might perhaps take this is a spicy one. I don't have the spicy emoji in this font. I might perhaps wait until with this one to the end. But yeah, let's just start. And again, feel free to ask questions in the chat or to unmute yourself. All right, so here we are asked to prove that. So if we have the circle and we go by the loop and then go backwards and then go forwards again, it should be the same thing as just going once forward, or it should be homotopy to that if you're used to homotopy theory or topology. So I will use equational reasoning that he introduced in the lecture, like this. So you say this is equal to this, which is equal to this, and then in here you provide the proofs that the two things are equal in each step. And I will do it as I would do it for myself. So the way I do equation reasoning is I just start with the left-hand side. Oh, sorry. There we go. And I do this thing, and then I put the right-hand side, and then I put the QED there. And then Control-C, Control-R to commit, or to it's Control-C, Control-R for refine, so that we only leave what a hole for the question mark. And how I usually do is just kind of, I haven't planned it out beforehand. Usually I just do it one step at a time. So let's copy this line, paste it down here, and then think, to me, what pops out is to change this into REFL. Yeah, so there's Control-C, Control-S for some sort of automatic theorem proving. I almost never use automatic theorem proving. I want to understand everything I do. But yeah, there's Control C, Control S. There's also Control C, Control A. Yeah, but I like knowing exactly what I do all the time. But if it's an easy goal, then yeah, Agda might be able to do it for you. All right, so yeah, we want to make this show that this thing is equal to this thing. And whenever you have like a sub expression that you're rewriting through an inequality, the thing you want to use is app. We can look at what it looks like. So like think of X and Y as your sub expressions, like loop composed with inverse of loop or REFL, and then F as whatever's outside it. So composed with loop in this case. So this is really nice. We can actually, Agda allows for operators to be partially applied. So this will be this thing. It's the same as writing something like, it's a function that sends P to P composed with loop. But I like writing it like this. Someone else might prefer writing it with lambda. And now we can see in the goal here that if I can prove that some things X and Y are equal, then X composed with loop will be equal to Y composed with loop, which is exactly what we want. So Control C, Control R. Okay, and now we are left with proving that loop composed with inverse of loop is reflexivity. And here we use results from the lecture notes. So here he proved a bunch of stuff about composing or concatenating paths. And the one we want to use is this one, right? So loop composed with inverse of loop is REFL. So let me just copy this. And then loop is the one we want to use it on. And now we can see in the goal that we have exactly what we need. So Control C, Control R. And there we go. That was the first step. Now here we can see the goal. We want to show that REFL composed with loop is equal to loop. But again, we have such a result in the lecture notes. And it is this one applied specifically to loop. So, and here we don't have to use an app because we are transforming the whole expression. Yeah, and then apply to loop. Let's see what we get. Yeah, we get the correct thing. So to see what you have, I press Control C, Control dot to see both the goal and what I have. That's very useful, I think. I use it all the time. Control C, Control R, and then we're done. So yeah. Right. Control C, Control A is auto that tries guessing, while Control C, Control S is filling out the things that are constrained to be exactly one thing. Yeah, right. Yeah, I never use Control C, Control S, so that's good. I don't know the exact difference between them, so thanks. Yeah, I guess maybe I should start using it. It sounds nice actually, because I just put an underscore because I can't be bothered. Yeah, maybe I should start using it. Thanks. Awesome. All right. Great. Let's do the next one. And I mean, this is the same thing now that we want to prove here. But it suggests that the exercise sheet that we can do it in two ways. So, well, we start in the same way. By the way, to make it neater. Ah, okay. Right. So let me try that. So there's a suggestion in the chat. I actually want to try that. So you put question mark. And then Control C, Control S. What's happening? Didn't I do that? Okay. C, Control S. Oh, okay, right. Yeah, okay. Control C, Control S. Right, okay. So that's actually really nice. Thanks for that tip. I've been doing Agda for 2 years, but I haven't done it this way. This is really handy. So that was awesome. Thank you so much. Okay. Well, it removed the parentheses because this is infixed to the left, but I'm adding them in for clarity. So how could we do this differently? Well, we could use associativity to instead group these two together and then eliminate those to REFL and then get loop in the end, this loop. So let's try to do that. So there we go. And let's move the parentheses. And this one here. Okay. So that's one step. Let's use from the lecture notes the fact that, or the proof that concatenation is associative. And here, this isn't exactly what's in the repository. I have changed it to not pattern match on either P or Q. I think in the lecture notes, he also pattern matches on Q, but that's not necessary because concatenation is defined by pattern matching on the second argument, and then it will reduce to the first argument. So here, it's enough to pattern match on R, because then this thing will reduce to Q, and then the whole thing will reduce to P composed with Q. Here, this with this as REFL, this will just reduce to P composed with Q, which is then the same thing on both sides, and then we use REFL. Anyway, we will use this. There it is. Okay, and now we need to, well, can I maybe do Control C, Control S here? So right, so I don't know if you remember from the lecture, but the thing that we are pattern matching on, Agda will usually not be happy to infer. So I guess let's give the last one, R here, explicitly, and that would be loop. No, let's see. Right, okay. This didn't work because if we look at what we have, it's actually we want the equality in the other direction. So we need to put exclamation mark there. And now we can refine. Okay, and now let's try Control-C, Control-S. Yes, amazing. This is so nice. Control-C, Control-S. There we go. And let's see, can you do it with this one? Control-C, Control-S. Oh, it can. Awesome. This is so nice. You've changed my life. Thank you so much. Okay. Right, and now we want to use the fact that this is equal to reflexivity. Let's copy and referral and make it line up. There we go. All right, so well, if you're observant, you will see that the goal, this looks like something different than this, but the reason for that is because, as I said, concatenation is defined by pattern matching on the right, so this one will be definitionally equal to just loop. But it's more readable, I think, to put it here. So, okay. Here again, we want to rewrite a sub-expression. So we need to use this app. In this case, what's outside of the sub-expression that we're changing is loop concatenated with. And here now, we will use, let's see, this one, proving that if you take the inverse to the left, then you get refl. And then we apply it to loop, and we see that we get the correct thing. So Control-C, Control-R. Okay. And now here we see that we have loop equals loop again, because this one reduces to just loop. But so the thing we have here is refl, let's see, refl loop. So this step can actually be skipped if you want to. But it just adds some readability. Yeah, and that was those two. Are there any questions so far? Okay. I don't see any questions, so let's continue on. Maybe I should go a bit faster if we want to get through some stuff. Yeah, this is a spicy one, so I think I'll save it, see if we have time. But otherwise, you can find the solutions on GitHub. So if I don't have time to go through them, it's not the end of the world. You can still find them. Okay, I think this one is nice. We use the fact that functions are group homomorphisms. If we think of the group operation as path concatenation. Yeah, state and prove a general lemma about what app of a function on the inverse of a path does, and also what is the inverse of two concatenated paths. Let me start with this one to see why we need this. So, all right, I will do it a new way. Okay. What we would like to do, well, I don't know how much intuition you have about what is supposed to happen here, but the idea is that if you use app on the inverse of a path, you get the inverse of app of the path. So that's what we're going to use here. And we see that it type checks at least, so that's nice. Now, of course, we haven't proved that this is the case actually, but we will. And then, so what is app double? Well, double sends loop to loop concatenated with loop. So this applying this function to loop should of course return loop concatenated with loop. All right, and then, so now I'm writing out the steps beforehand and then trying to fill in the proofs for each step later. Now, the inverse of the concatenation of two paths should hopefully be the inverse of the second one concatenated with the inverse of the first one, but both are loop in this case. So, oh yeah, that's the goal. Ignore this step. There we go. Okay. Let's do the step we can do. So, solutions. Yeah. So we want to rewrite this sub expression to this. So we need to use app with the exclamation mark. Now we need to prove that app double loop is loop composed with loop. So here we need to use one of the recursion principles for S1. In this case, it's this one that we have to use, which says that if you define a function by S1 recursion, then if you use app to apply that function to the loop, you get back the second argument that you used to define it. And double is defined like this. So the second argument is this thing. So it gives us what we want. So S1 rec loop. And now we need to give the arguments that double was defined with. So sending base to base and sending loop to loop concatenated with loop. And now we see in the goal app of this thing applied to loop is loop composed with loop. And this thing is exactly double. So this should work. Yay. All right. Now for this one and for this one, we need the two things that they suggested we prove here. So let's do it. So okay. This is how I usually write up my stuff. I write what I want to end up with. I want to say that app f to the inverse of p is equal to the inverse of app f p. Yeah, you could see that this type checks. Well, we could do it easily. Okay, so if p goes from x to y, then app f inverse of p will be a path from f of y to f of x, and similarly inverse app fp will also be a path from f of y to f of x. So at least it makes sense that it type checks. Okay, and now I fill in everything I need for this thing to make sense. So I need some P saying that X equals Y. And for this, I need, of course, some X and Y of some type A. And for this, I need a type A. I also need a function. So f from A to B. And for this, I need B as a type. So if you do it this way, then it could be easier to remember what you need to add as the arguments. Okay. Right. What can we do? I mean, whenever you prove something with an equality, with variables for endpoints, then it's a good idea usually to pattern match on P. So Control C. So when it's reflexivity, and then what we need to prove is this. Because then it's reflexivity, so then the app just becomes reflexivity. Everything just becomes reflexivity. It's that's usually how it is when you pattern match on identity types. Awesome. Okay, so that one is done. Then we can use it here. And then loop. And then we get what we want. Well, we haven't given the function, but it's going to should be able to figure that out. So Control C, Control R, and there we go. Amazing. And then let's do the other one, which says what happens with if you take the inverse of two concatenated paths. And now I think I'm just gonna paste the type here. So we have a type A, we have 3 points, and we have a path from X to Y, path from Y to Z. And we take the inverse of the concatenation should be the concatenation of the second path inverse and the inverse of the first path. We could check again that this type checks, but in the interest of time, I'm not going to write that out right now. Okay, now we have two paths here that we could pattern match on. So you could pattern match on both, but I think in this case, it's actually, do you need to pattern match on both? Yeah, I think you do actually, because the concatenation only computes when you have REFL on the right. And in this, on this side, that will be Q. You only pattern match on P. Yeah, but then you need to use one of the results here. Yeah, exactly. So that's one way of doing it. Let's do that. If we only pattern match on P, then this thing will not compute. Let's see what happens. And then we need to prove that inverse of REFL X concatenated with Q is inverse of Q. And then we need to use app and then use the unit law because this thing doesn't reduce. So what I did was just pattern match on both. And then everything just becomes REFL. Yeah. Okay. Great. Now we can use that one here. So applying it to loop, and then we get exactly what we want. Awesome. Are there any questions so far? Okay, then I will move forward. Just write any questions in the chat or unmute yourself. Okay, so we want to define a function invert such that app invert inverts the path on the circle, i.e. sends the n-fold loop to the minus n-fold loop. So let's recall the recursion. So this is the one we use to define a function out of the circle, S1. So let's use that one, S1 rec. Okay, let's Control-C, Control-R, and it will tell us what we need. So we need to say where the base point is sent, and of course it's going to be sent to itself. And then we need to say where we should send the just one loop, and that should be, of course, to the inverse of loop. And then everything else follows from this, that the n-fold loop will be sent to the minus n-fold loop. You could do something like this, for example, to check that this is the case for some like specific example. You could see where loop composed with loop is sent and prove that it's sent to inverse loop, inverse loop, inverse loop, if you want to. So that's an optional extra exercise, but I'm not going to do that now. I will move on. Yeah. Now, I don't remember if he got to this point in the lecture, but he defines a function from, so first of all, he defines another kind of circle, which has 2 points, and then a line, 2 lines between them, which like intuitively, has the same shape as a circle. You just split it up in 2 kind of. So it should be the same thing. So he defines then functions back and forth between S1 and circle 2. And now we should prove that if we do 2 and then from, we get back what we should get back. So 2 goes from S1 to the 2-point circle. From goes the other way. Okay. So yeah, let's see here. If we can Control-C, Control-N to normalize. So to base normalizes to north, and this is because we have added this rewrite. Where is it? This thing is the reason why this normalizes. So if we apply an S1 rec defined function to base, it will compute to this first argument. Okay, and then we have a similar rewrite for the 2-point circle. This one that says that if you apply circle 2 rec function to north, it will compute to the first argument. So Control-C, Control-N to normalize, and we see that we get base back. So this is actually base equals base. And here I suggest using REFL base. So here we see how nice it is to have these rewrites. Then this thing computes. Otherwise, it would be a bit more complicated. Okay, but this one will still be complicated. we can think of the types here if we want to. So app to loop will go from to applied to base to applied to base. And both of these will compute to north because of the rewriting rule. And then if we do app from on this, we will get something that goes from north to from north. And these will, because of the rewriting, compute to base. Okay, just so we know that this, well, we know that it type checks because Agda doesn't complain, but this is why. So these are the same type. Okay, here it's a bit more complicated. So let's start doing some equational reasoning. All right, see what we can do. Now, the thing is that applying a function, the functions to and from to the points computes, but it doesn't when you apply to paths. So we need to do this. Okay, what can we do? Well, first of all, let's rewrite this expression. So let me copy this. Now, what should this become? Well, 2 with this is what we should send loop to. So doing app 2 on loop should return this thing. So that's what we should put here. Any type checks, that's always a good sign. See if we can also prove it. Here is where there was, this can be confusing. So we want to rewrite the sub expression, which means that we need to use app. And the argument to app should be the outer expression, which in this case is app from. So 2 apps in the same line, which can be confusing, but yeah, it's just because we this app is part of the thing, the outer expression. All right. Now we want to show that app to loop is equal to east composed with the inverse of west. And for this, we need to use one of the computation rules for the circle. Yeah, so this one that says that app of the function applied to loop should be the second argument. So S1 rec loop. And now here we need to add put the arguments that we used to define 2. So north as the first argument and this thing as the second argument. Okay, so that one is the thing that shows that this actually is equal to this. Okay, awesome. Now we can use something we did earlier. No, this is actually in, sorry. Yeah, this is something in the lecture notes. I had to look at my solutions. So we want to say what happens to when we do app on a concatenation. And this is already proved in the lecture notes file. If you do app on a concatenation, it's the same thing as concatenating, doing app on both of them. So we should be able to use that for the next step to get this app from east concatenated with app from inverse west. Making it neater. Was it mentioned in the lecture why we can't use rewrite for the loop rule as well? Yes, I think actually twice, because he mentioned it while he was talking about the rule, and then there was also a question about it. Essentially, what he said was that it's not very useful. When you start doing stuff where you need to use that rule, you will, as this is my rephrasing of what I understood he said, then when you need to use it, you're usually in a scenario where you need to use a bunch of path calculus anyway, so it doesn't turn out to be very useful. Yeah, but the lecture should be on YouTube, so you can watch his original answer instead of my rephrasing. But yeah, good question. Okay. Now let's see. Here we don't give the function, but we give the paths. So that's east, east, and inverse west. Okay, great. Now we need to use again a computation rule that says how this one behaves, but now it's a circle 2 computation rule instead of a S1 computation rule. And we can also rewrite this, the other thing. We can rewrite both of these in one go. So this one should reduce to what we decide to send to east, which is this thing. This is what we send east to. So it should reduce to the loop, or it should be equal to loop. It should not reduce because we don't have a rewrite for this. And this thing, we can use our lemma that we had before that says what happens if we do app on the inverse of a path. So we get the inverse out from there. So it should be inverse of app from west. Of course, I need parentheses. Awesome. Okay, so now we can use this nice, convenient app2 that allows us to change two sub-expressions at the same time. So in this case, we can do like this. And then let's see what this gives us. So if we prove that x equals x prime, y equals y prime, then x concatenated with y equals x prime concatenated with y prime. So that's really nice. And now, well, here, yeah, it doesn't say what it is we need here, but what we need is to prove that this is equal to this. And for that, we use the circle to rec east, which says what happens when you apply circle to rec function to east. Now we need to give all the arguments that we used to define from, which is base, base, referral base, loop. So we put it there. and Control-C, Control-R. Yay, it works. And here we just use, as I said, the app inverse west. Yeah, Control-C, Control-R. Awesome. Okay, and now we, let's see. Yeah, we can rewrite this thing. That should be what we sent to west, so REFL base. Or sorry, what we sent west to, rather. So here we want to rewrite, let me do another line. Well, it's actually, we can actually write the argument here. REFL base. This is what west should be sent to. So here, again, we're rewriting a sub-expression. We need to use app. So app, here, we can't do the nice underscore notation anymore because we have this exclamation mark here. So we need to do something like the function that sends P to loop concatenated with inverse of P. And now we see that we need to prove that app from west is REFL from north. Yeah, but from north will be base. Will compute base. So here we need to use the corresponding thing as here, circle to west, though, instead of east. So let me just, I think this is the quickest way to do it. West. There we go. And now, well, if you look at the goal here, it's loop equals loop, and that's because this thing computes to REFL, and then concatenation with REFL to the right computes to the left thing. So this is just REFL here. So this step can be skipped, but it adds some readability. Okay, so this was a couple of steps. There's 3 minutes left. So I think I will ask you guys if there's anything you would want to see, because obviously I can't do them all. Maybe one of the spicy ones, or do you want to see? Yeah, is there anything in particular you want to see? As I mentioned before, there's some suggested solutions on GitHub, so you can look at those as well. But yeah, I can show something that's particularly interesting, maybe. Anything you struggle with, maybe, that I could perhaps explain? I was wondering about what the trick was for the first spicy one. That said, wait until later. Right. Okay. Since no one else said anything, let's talk about. So, do you mean this one? Yeah. Yes. The trick is to do this for an arbitrary path P instead of in particular loop. And the reason why that's nice is because when you have an arbitrary path, you can do path induction on it. And then that's REFL. And then usually when you do path induction, well, if you're lucky, everything just computes down to REFL in the end. So that's the secret trick here. So let me do it and show what's going on. Let me just bring out my notes so that I know what I'm doing. Okay. And I'm going to put that general case in a where clause. So I'm going to name it the same thing as I did in the solutions sheet. So I want to prove a more general result and then just apply that in particular to loop. So maybe I should actually, instead of just putting everything there. Okay. We want to prove that the two proofs, homotopy 1 and homotopy 2, are equal. And the two proofs there are this concatenated with this, because equality reasoning, what it does in the background is concatenate the paths here. So the term homotopy 1 is this concatenated with the next step here. But now we want to do it for an arbitrary path P. P. Yeah. And then let's see what we need. Yeah. So we need another proof now that P concatenated with inverse of P concatenated with P equals P. Yes, and that proof is all of these steps concatenated, so, but with P instead of loop. So we're doing it more generally. Concatenated with this thing, but with P instead. And then, yeah, well, we don't need to have REFL here. Again, because having REFL here will just compute to nothing. So, or the thing we had to the left. So, yeah, now we want to prove this more generally. And this is now the trick, because now this is an arbitrary path between two arbitrary endpoints. And that allows us to pattern match Control C, Control C. And then we end up with the same thing on both sides. Everything just becomes REFL. Best thing in the world. And then we just do REFL. Super nice. And then to prove that homotopy 1 equals homotopy 2, we just use gen in particular for loop. And then in the goal here, it doesn't show what homotopy 1 and homotopy 2 normalize to, but it will be this thing and this thing. So let's Control C, Control R, and it works. Is it necessary to use this trick, or does it just make it easier? Yeah, I was actually thinking about that myself. It definitely makes it easier. I was thinking if it's possible to do it without it, to do it in particular for these two. Maybe you can if you use some. Yeah, someone says, I think it's necessary, but not completely sure. Yeah, I guess maybe. Yeah, I think it's necessary. Or maybe you could have some lemmas about, but how to, that kind of gets you from here to here. Yeah, maybe you could use some lemmas about path computation that could get you from here to here. But this is definitely much easier. So I guess my answer is it might not be necessary, but it's definitely much easier. Another question, what's the geometric / topological intuition for why this trick works? Right. Yeah, okay. I don't know if I have a good intuition, topological intuition actually for this. I more think of this just as that I can pattern match on breadthful when I have two variable endpoints, and I can't do that when I have them fixed. And the question, I guess, then becomes, what is the intuition for that? Which I don't think I'm the correct person to answer that. Maybe ask it in the Discord for someone who is more into like the topological or homotopical intuition behind all this. That helped. I don't feel like I answered, but okay. Awesome. Okay, I will stop the recording now. If I figure out how to do that. 1 second. Stop recording. Okay.